Okay, let's look at applications of determinants. Commented in the previous section that determinants actually predate the idea of matrices, which is pretty weird, but they came into the picture in terms of solving systems of equations. So let's see how that works. And we'll illustrate this with some solving of systems of equations. It's a horribly inefficient way of dealing with systems of equations. This section's probably a touch more of theoretical interest. But anywho, we'll illustrate some of the theoretical ideas with some small systems of equations. Large systems of equations, this approach is just totally unwieldy. So section 4.3 is computation of determinants and Cramer's rule. So the plan here is to a couple of things: to relate the computation of determinants to elementary row operations, and we've already done some of that in the previous section, and to use determinants to solve systems of equations. This is a computationally complex, as the book says, way of dealing with systems of equations. This ain't the way to solve a system of equations. You have an excellent way of solving systems of equations, Gauss-Jordan elimination. So mostly of theoretical interest, the results of this section, but let's see if we can make some sense out of them. First, in terms of computation of determinants, this is really just a restatement of some of the things we had in the previous section, one little twist. The determinant of an n by n matrix, we only have determinants of square matrices, just like we only have inverses of square matrices. Determinants can be computed as follows. Take matrix A, reduce it to an echelon form using only row addition and row interchanges. Secondly, if any matrices appearing in the reduction contain a row of zeros, then the determinant is A. Otherwise, and if we get to this stage, then it must be that the row reduction has worked. The matrix will be an upper triangular matrix with n pivots, and the determinant of that matrix will be -1 to the r times the product of the diagonal entries, the product of those pivots, the product of the diagonal entries. Some could be 0, where r is the number of row or, turns out, column interchanges. You know the determinant changes by a factor of -1 every time we have a row interchange. And this is the technique we used in the previous section, but they've parenthetically stuck these comments in about column interchanges, column addition, column of zeros. Hey, you know, if there's a column of zeros, then we've got a determinant of 0, because we could take the cofactor expansion for the determinant along that column of all zeros. In fact, we would enthusiastically do so because arithmetic's easy. But we've never done column addition, we've never done column interchanges, and we won't. But there are people out there living perfectly happy lives doing the same kind of elementary row operations we did, but doing them to columns. We hadn't needed them, we won't need them. They are out there. If there's any place to talk about them, it's maybe here. There's some things called permutation matrices, which allow us to manipulate a matrix in terms of permuting the rows around. We've seen elementary matrices, a product of certain kinds of elementary matrices produce permutation matrices, but we've seen where multiplication on the left by an elementary matrix results in an elementary row operation. Well, it turns out multiplication on the right by an elementary matrix produces a column operation. And I may have mentioned that in passing when we dealt with elementary matrices. But suffice it to say, hey, there's such a thing as column operations as well. And let's just leave it at that. And we'll stick exclusively with row operations. But for your future reference, yeah, there's some other stuff out there. So this is roughly how we had computed determinants in the previous section. The strategy is row reduce, get zeros, maybe do some swapping around, some interchanging of rows, produce an upper triangular matrix and go to town taking products of diagonal entries. Oh, it'll be affected by how many row interchanges you had, and it'll be affected exactly like this. -1 to the r, where r is the number of row interchanges. So that's actually rehashing some old information. Let's illustrate one more time this technique. So let's look at number 6 from the section. Find the determinant of, okay, it's a big matrix. I ain't too afraid now that I got this row reduction stuff at my disposal, and I got a fair number of zeros in it already. Okay, so plan is to find the determinant of this 5 by 5 matrix. Okay, I'm attracted to this first column, maybe this first row as well, because of all the zeros. Let's follow that protocol we just mentioned, though, and turn this into an upper triangular matrix. So we could use the 3 to eliminate the -1. I don't like the sound of that because I see some fractions coming if we're going to do this by hand, which with a clicker we effectively are. Maybe we'll swap some things around and then do an elimination. And let's see, this entry catches my eye and this entry catches my eye. So we've got these 3 entries in the current form of the matrix that are keeping it from being an upper triangular matrix. So let's take care of that. Okay, so let's take the given matrix. I tell you what, let's swap rows 1 and 2 for reasons just mentioned. Oh, that'll change the determinant by a negative sign, as you know. So to get equality here, I need a negative sign out front. All right, we just swapped the first 2 rows, and we did so I could use the -1 to eliminate the 3. Through the elementary row operation, take row 2 and replace it with row 2 plus 3 times row 1. That'll introduce a -3. Add it to this, we'll produce a 0 down here. It produces some other stuff as well. Trust me on the arithmetic. But let's use the -1 to eliminate the 3, gets us closer to lower triangular. And I tell you what, we've rarely, if ever, done this. At the same time, let's use this 1 to eliminate this -1 and use the elementary row operation. R5, row 5 is replaced with row 5 plus row 4. We've been super hesitant to do 2 row addition operations in the same step. We're okay here because the first one involves row 1 and row 2, and the second one involves row 4 and row 5. So in a sense, they're kind of disjoint. So doing both of those produces still not quite an upper triangular matrix. We've got a pivot, oops, a pivot, and a pivot. This -3 entry, we need to get rid of that. Following the protocol we just mentioned, let's use the 14 to eliminate the -3. So we put off fractions as long as we can. One option is to divide this second row by 14, make this a 1. Oh, but then we get a 3/14 over here. So 6 of one and half a dozen of the other, we're going to have some fractions, at least temporarily. All right, so recopying where we left off, let's use the 14 to eliminate the -3. So we'll have to take row 3 and add to it 3/14 times row 2. Okay, 3/14 times 14 is 3. Add it to -3, produces a 0. Here we get what? 9/14 plus 5. 5/14 is 70/14. So do the arithmetic. We'll get 79/14. So I'm somewhat apologetic about the fractions, but it looks like they were largely unavoidable following the protocol we want to follow. Anyhow, upper triangular matrix. So you want the determinant of that. Don't forget the negative sign out front. All we have to do is take a product of the diagonal entries. And fortunately, there's a 14 here and a 14 in the denominator here. So we actually get a nice whole number out. It looks like we get out 474. Example 4.2.4 says upper triangular matrices have determinants that are products of their diagonal entries. All right, so there you go. What does that tell you about the original matrix A? The fact that it has a determinant of 474. We know a little bit now. Tells you, well, the determinant's not 0, so it's an invertible matrix. So we've got that going for us. So at least we know that much about it. Otherwise, that particular value of 474, so far at least, not much information there. Only the fact that it's not 0. All right, we're going to introduce now in Cramer's rule a way to solve a system of equations, ax equals b, assuming the coefficient matrix is invertible, which is effectively, as you know from your experience with systems of equations, is effectively assuming there's a unique solution. The technique we're going to use produces this unique solution in terms of determinants. Okay. You like that? No, I don't like taking determinants. And this is going to require a bunch of determinants. We'll illustrate it in a small system of equations just to make sense out of what it says. Cramer's rule claims, consider we have a linear system, ax equals b, where A, coefficient matrix A, has the usual entries, a sub I, j, is an n by n invertible matrix. Okay, so that assumes the determinant of A right there is non-zero. Good thing, we're going to be dividing by it downstairs. Let vector x have the usual components. Let vector b have the usual components. The claim is the system has a unique solution, and it is given by x sub k equals the determinant of matrix b sub k divided by the determinant of matrix A. For k equals 1 through n, so this gives all values of the unknowns, x sub 1 through x sub n, and this matrix B sub k, this matrix B sub k is the matrix obtained from matrix A by replacing the kth column vector of A by the column vector B. All right, so for example, for B sub 1, we'll take matrix A, replace the first column with this bunch of B values. Take a determinant of that matrix, that'll give us the numerator here, and take the determinant of matrix A. So to apply Cramer's rule, you need to take the determinant of matrix A, that's one determinant, it's an n by n matrix, if n is big, it's nightmarish, and you need to take a determinant of matrix B sub 1, okay, it's also an n by n matrix, matrix B sub 2, and so forth. You got to do this for k equals 1 to n. You got to find n plus 1 determinants of n by n matrices, n for the b1 through b sub n, and A itself. So n plus 1 determinants of n by n matrices. And your experience with the previous sections tell you, just taking determinants is time consuming. This is a time consuming way to solve a system of equations. There's a proof for it in the notes. Let's gloss over that. And let's look at number 26 and try to illustrate this idea of producing the B sub k's. Let's also keep that system of equations fairly small. Proof, here's a proof. Here's actually a production of a particular matrix. This isn't one of the B sub k's, but it's a similar technique. So I leave it to you to enjoy reading that proof. Let's illustrate it. Okay, so use Cramer's rule to solve this little 2 equations and 2 unknowns. Okay, we'll introduce our notation. Coefficient matrix, 3, 1, 2, 1 for the rows. The B vector, right-hand side of the equations, 5 and 0. The X vector is the unknowns, x1 and x2. So we're looking for x1 and x2. To create vector B sub 1, take matrix A, B sub 1, first column, replace the first column of A with vector B, the 5 and the 0, 3 and the 2, replace with the 5 and the 0, producing this thing. So B sub 1 is this 2 by 2 matrix. B sub 2, we'll take matrix A, replace the second column, the 2 1s, with the B vector, the 5 and the 0, and there's B sub 2. So that's what they mean by creating these B sub k's. Next, we need the determinant. We need the determinant of matrix A. Easy enough. Well, these aren't bad determinants here because they're just 2 by 2 matrices. And by the way, I've mentioned historically, this is where determinants came from. So this gives a manipulation that produces some algebraic results that give solutions to systems of equations. They express them in terms of these things called determinants. This came before matrix stuff and the row reduction stuff, in fact. Anyhow, determinant of A, easy enough, 3 times 1 minus 1 times 2, that's 1. We'll need the determinant of B sub 1, 5 times 1 minus 1 times 0, 5. Determinant of B sub 2, 3 times 0 minus 5 times 2, 0 minus 10, negative 10. So we get determinant of A is 1, determinant of B sub 1 is 5, determinant of B sub 2 is negative 10. Kramer's rule tells us X sub 1 is determinant of B sub 1 over the determinant of A. 5 over 1 is 5. X sub 2 is a determinant of B sub 2 over the determinant of A. Negative 10 over 1, negative 10. There's your X sub 1, there's your X sub 2. There's how Kramer's rule works. And that ain't so bad for 2 equations and 2 unknowns. When we first encountered 2 equations and 2 unknowns, we solved them just by fiddling with them because we didn't have any of the matrix techniques yet. 2 equations, 2 unknowns, that's not a big deal. We go to 3 equations and 3 unknowns. Now you're taking 3 equations and 3 unknowns, that'd be 4 determinants of 3 by 3 matrices, and determinants of 3 by 3 matrices isn't that unwieldy, but it's a little clunky to deal with, especially if we got to do 4 of them. But that's what Kramer's rule would give us, were we to deal with bigger systems of equations. Back to the notes. There's a cute quote in our textbook. So we just saw for 2 equations and 2 unknowns, we needed 3 determinants of 2 by 2 matrices. If we use Kramer's rule for 3 equations and 3 unknowns, I just told you that'd be 4 determinants of 3 by 3 matrices. Fraley and Beauregard describe what would happen in 10 equations and 10 unknowns. That'd be 11 determinants of 10 by 10 matrices. And I think they give some little counting arguments of how much arithmetic that is. And the book states on page 268, this illustrates the folly of using Kramer's rule to solve systems of equations. So it's of a theoretical interest. There's how it works. Nobody's going to solve a system of equations, a specific hands-on system of equations using Kramer's rule, unless it's 2 by 2. Even then, there's ways that are no more complicated than Kramer's rule. For 3 by 3, it's definitely more complicated with all this determinant stuff. Now let's end right there briefly, and we'll come in and I'll do a part 2 to this section, and we'll pick up with some other things, something called an adjoint of a matrix. So I'll see you shortly.